Hello, everybody. Hello from McDonald Observatory. My name is Stephen Hummel. I'm going to be your host tonight for our Deep Sky Live tour, where I'm going to be showing you a few of the interesting things that are in the sky right now. Very, very distant objects I have for you tonight, far beyond the reaches of our solar system. But I'm coming to you from McDonald Observatory, and McDonald Observatory is a research branch of the University of Texas at Austin. And if you have never visited us, we are located out in far west Texas. I have a picture of us during the daytime. So we have several major telescopes here at McDonald Observatory, the one in the foreground being our largest, the two in the background being our 107-inch and 82-inch telescopes. But the one in the foreground is currently the largest telescope in the world that's operational, because unlike most observatories in the world at the moment, we are still open and doing research during these times. The telescopes, at least a few of them, are still collecting data. They're setting up for tonight as we speak, that's something that we've worked very hard to maintain, and we hope to keep running throughout this pandemic for as long as possible. But I am down at the visitor center of McDonald Observatory. And if you have never visited us, if you do come and pay us a visit, you'll likely come to our visitor center. We have some telescopes down here. You can see our arrow there. That is the telescope I'm currently located inside. That's the dome I'm currently located in. And if you come visit us for a star party, then you'll have a chance to look through these telescopes as well as several others. And again, the telescope is right behind me. This is one of the telescopes we use for public viewing. It's not necessarily used for research. However, it is a research grade telescope. It is certainly capable of research, should we choose to use it for that. However, we mostly use it for fun, for pretty views and things. And the targets we're going to be looking at tonight are generally speaking, very faint, very dark objects. And you have to have dark skies in order to see them. And I want to talk a little bit about why we are located out in the middle of far west Texas here at McDonald Observatory. And that's so that we are far from anybody. Here's a map of Texas and kind of northern Mexico there, and a map of how bright the sky is in any given location. And you can see that where McDonald Observatory is, we are pretty far out there, kind of in the middle of nowhere. And that's exactly how we like it. Far from major urban centers, that means we have very dark skies. We have some of the darkest skies of any major observatory in the world. However, you may notice that glow up above where we are to our north. And if you know your geography of Texas, you know that there isn't really a major city where that big glow is. That's all light from the oil and gas industry. And we are working with the oil and gas industry there in the Permian Basin to try to keep the skies dark for the coming years. It's actually part of my job here at McDonald Observatory. And in fact, this map may already be out of date. This data is from 2019, but with the current shakeup in the oil industry at the moment, it could be a different story now. However, generally speaking, we think it generally resembles that to our north. All right, but uh, throughout McDonald Observatory's history, we have had incredibly dark skies, and that really is so important because, again, if you want to do astronomical research or see some of these things in the sky, you have to have very very dark conditions. And so, if you're worried about what you can do about light pollution and how you can help us, you can go to our website under Learn. You can read about our Dark Skies Initiative. That's under the Learn tab on McDonaldObservatory.org. But the first object we're going to look at tonight through this telescope is known as the Eskimo Nebula. Actually, it's got a lot of different names. I particularly don't like that name, Eskimo Nebula, but its other more common name I think is even worse. It's also known as the Clown Face Nebula. I'm not really a fan of clowns either. So usually I just call this object by its catalog number, which isn't exactly catchy, but it's NGC 2392. NGC 2392. I know that's not something you're going to probably remember when this program is over, but that's what I prefer to call it. And so we're going to look at that with a camera here attached to my telescope. Again, this is a 16-inch telescope. And if you're curious about the specs of this, they're in the description down below. Also, if you have any questions, I should add, during this program, you are welcome to ask those questions in the chat, in the live chat. And we have a team of moderators who are willing to and more than capable of answering any questions you may have. However, if it's a question that we think is really good or it just can't be answered in chat format, I will be taking more questions towards the end. You can send those questions to the moderators anytime, and they will also let me know at the end. So if you got any questions, again, don't be shy. Moderators are in chat to help you out. All right, but on the back of this telescope, we got a camera, and that camera is going to be taking some exposures of these targets. And the first exposure I'm going to take is going to try to mimic what the human eye would see through the telescope if you were to just simply look through the telescope with an eyepiece, with the human eye. Then the second exposure I'm going to take with the camera is going to be much longer, and it's going to gather a lot more light than our eyes could ever see in a moment. It's going to show you a lot more detail. Now, if you've seen pretty pictures of these objects online, those are most likely many hours worth of exposures. We're going to be taking a few minutes, but I hope that'll give you a little more context and kind of see what these objects are really like and how they really appear in reality compared to very long exposures. It's kind of hard to put that into context in the sky. All right, so again, if you have any questions, be sure to ask them in chat. But the Eskimo Nebula, or Clownface Nebula, or NGC 2392, is located in the constellation of Gemini. And Gemini is also known as the twins here. Then you can ignore this here. This is just the middle part of the sky. But at the moment, it's kind of in the west from where we are at McDonald Observatory. And the Eskimo Nebula is a very, very small object. You need a lot of magnification in order to see it well. It's really quite tiny. But here is the view of the Eskimo Nebula right now. This is again a live view fed from the camera. And you can see that this is refreshing every 3 seconds. And so that's going to remain there throughout the program. You'll see that the image will be refreshing. So this is kind of what it looks like in the telescope when you just look at it with the human eye. It really does look like that. And what it really is, what this object really is essentially a shell of gas that's expanding off of a star right at the center. And this star was once very similar to our sun, how our sun is today. And we call this kind of an object, this classification of an object, a planetary nebula. Planetary nebula. And that's a very confusing term. Because that's a very old name. Early astronomers, when they looked at objects like this, they saw this as, well, maybe it's kind of where planets come from. Maybe it's where planets are being formed or something. And we quickly learned that's not the case. But the name stuck. We still call this a planetary nebula, just because it sort of looked like maybe that's like a planet or something, or maybe that's where planets are from. And nebula simply means cloud. That's all it means. It's basically just cloud. What's really going on here is this star has essentially run out of fuel. And again, it was a star that's kind of like how our sun is today. And stars are fusion reactors. They're taking hydrogen and fusing it into helium at their cores. And that process of nuclear fusion creates a lot of heat and energy, and that's what's powering a star. But eventually, it runs out of hydrogen to use as fuel. And when it runs out, that process kind of breaks down. And so what ends up happening in the later part of a star's life is it begins to puff up and expand. And I have a little animation of that. If you were here for the last live stream, you're probably familiar with this animation because we looked at another planetary nebula. But they puff up, they expand, they blow off their outer layers. And there's all this gas and debris kind of floating off, gently expanding off from that little star. Again, it's not an explosion. Although it's not a very nice process either. You wouldn't want to be on a planet orbiting that star. But all that debris that was cast off is now kind of forming this general haze, this glow around that star. And the heat and radiation of that little star is exciting the gas it gave off and making it glow. And that's what we're seeing here. But a lot of planetary nebulas look different. This particular one has a fainter outer shell, and there's also a brighter inner ring. And the reasons why these objects often look different are kind of debated, but it's thought that perhaps this particular star had another star orbiting around it very closely. And so what was going on is that as that other star orbited around the bigger one that was dying, the material the bigger one was shedding off kind of got turned around, and it's forming this pattern that we see here. So if this also, it may look different from a different angle. This is what some people currently believe about this object. That if you view this kind of 90 degrees from where we are now, it wouldn't be a ring, but more of two jets pointed outwards. And those jets happen to be kind of facing us, and we're kind of looking down that. So this is a relatively slow process that this star dies off. It's over tens of thousands of years. But the star maybe lived several billion years before it reached that point. And eventually, when our sun runs out of fuel in 5 billion years, so don't worry about it, right? It'll do the same thing, or roughly the same thing, that this star is currently doing. All right, let's take a longer exposure. And this is only 3 seconds. Let's go for 8 seconds. I'll bring out a little more. This happens to be one of those targets that, honestly, it doesn't look all that different if you expose for a long time. But you can see I've brought out a little more detail now. And you can see that there is a little bit of a kind of a brighter part here. And the reason it's called the Eskimo Nebula is some people think that sort of looks like a parka, like someone's kind of wearing something over their head. I don't really buy that personally. I think it is. I think it looks like a cyclops eye, and this is kind of his eyebrow, you know, and that's his eyeball. That's how I see it. So if we were to change the name, I would call it the Cyclops Eye Nebula, just personally. And maybe we can get that to catch on. But this is about 5,000 light years away from us tonight. 5,000 years for that light to travel from this object to us. And so we see it as it was 5,000 years in the past. All right, so that was NGC 2392, or the Cyclops Eye Nebula, as I call it. But we're going to move on now to a different object. And this next object is also a kind of remnant of a dying star, but it is very different conditions. And I'm moving the telescope here behind me. I'm going to move the dome now as well in a second. There we go. I've moved the dome to be in line with the telescope very roughly. And this next object is known as M1, Messier 1. And I talked a little bit about Charles Messier in the last live stream earlier this week. But Charles Messier was a French comet hunter. He was looking for comets. And he was looking for objects that essentially were kind of faint and fuzzy, but moved across the sky. That's what a comet looks like. Well, he found lots of faint and fuzzy things, but they didn't move. And so he knew that they couldn't be comets. This was the first object he found like that. It was a faint fuzzy thing he kind of thought was a comet at first, and then it turned out it wasn't, because it wasn't really moving from night to night across the sky. But it's known as the Crab Nebula, and I think that's also another kind of silly name. You have to have an imagination to see these things in the objects. But the Crab Nebula is low at the moment in the west. It's going to set pretty soon. It's in the constellation of Taurus, most of which is very low, below my horizon here of the dome. But the Crab Nebula, well, it is a faint, fuzzy thing for sure. And this is kind of what it looks like in the eyepiece of a telescope. It looks like a faint, fuzzy blob. Very faint, actually. It can be a quite challenging target sometimes. But let's take a longer exposure. Let's go for about 45 seconds. And that should be enough time for the camera to gather light to bring out a lot more detail. What this really is the remains of a star that was much more massive than our sun. So smaller stars, like our sun, and smaller, form planetary nebulas, like we just saw, when they eventually die. Bigger stars, 8 times the mass of the sun or more, explode dramatically. Now, those big stars are relatively rare in the universe. There's a lot more small ones than there are big ones. But the bigger the star, the hotter it burns, and the more rapidly it's fusing hydrogen into other elements at its core. And because it's bigger and brighter, it burns out faster too. So the bigger they are, the faster they die out. And so here it is. We can see that it is kind of a knotted complex cloud. It's definitely a nebula, right? It's very, very nebulous, just kind of a big, vague cloud. But what happened here was that that star that was very massive exploded all at once. And I have a little animation of that event, which occurred, and we know this, because it occurred in 1054 AD. That star detonated all at once, not in a slow moment, but in a split second it exploded with a tremendous amount of energy. Now, most of that energy was in one tremendous wave, that bright flash, and that flash was visible to Chinese astronomers in 1054 AD. So they actually recorded that event almost 1,000 years ago. And what's left over is a shell of expanding material. And it's expanding quite fast, hundreds of miles per second, expanding away. And that's what we're seeing here, is this vague kind of cloud. And I can give a little more contrast to the image there. So what we're seeing there is, in fact, the expanding wave of material away from that little star that died about almost 1,000 years ago. And so what we're seeing is essentially materials that were generated in the heat and the moment of that explosion. It's very hot here, and especially towards the center. And in fact, elements heavier than iron, almost all the elements heavier than iron on the periodic table, are generated in these moments. So if you have gold or platinum or something, maybe you got a gold ring, that gold was formed most likely from a supernova explosion billions or millions of, or actually, yeah, definitely billions of years ago. That material expanded off and eventually found its way to the Earth and became part of our planet. So although that star may no longer be with us for the most part, its material will expand off and eventually be recycled and be part of future stars or planets, or who knows, or it may just float off into space forever. It kind of depends. But all that most of that star just was expanded off and is now expanding through space in this cloud. Not all of the star is gone. Some of it blew off, and what remained was compressed down into a tiny, tiny little object. And when we say things are small in space, we use that in relative terms. But this really is relatively small. The star, the husk that's left over, is about the size of Manhattan, and it's known as a neutron star. And it's kind of right here, right above my mouse. It's that little speck. That is what is left over of the star that exploded. It's an incredibly dense thing. If it were any denser, it would form a black hole, and no light would be able to escape. So that really is remarkable that we're even able to see that. The exact distance to this object, the Messier 1, or the Crab Nebula, is debated. This is actually one of the most well-studied objects in the entire sky, and yet we can't agree on an exact distance. It's somewhere around 5,000 light years plus or minus 1,500 light years. So that's a pretty big range, pretty big error bars there. We definitely need to study this object a little more to really be certain. But although that little star at the center, just a little faint speck, is maybe around the size of Manhattan, the cloud is several light years across now. So the cloud, and it's going to continue to expand, is a quite large object. All right, so this was M1, and now we're going to switch to another different object. So both those objects I just showed you were within our own galaxy, our own Milky Way galaxy. The next object, the next three actually objects we're going to look at are other galaxies, and so they are things that are incredibly distant. And you can see the telescope moving behind me. I'm going to start moving the dome as well. So the next object we're going to look at is known as M51, or the Whirlpool Galaxy. And it's a fantastic example of a spiral galaxy. Now, we also live in a spiral galaxy, the Milky Way. But this is a very, very dramatic one. And it is extra spirally, I would say. And it's going to take a moment for the dome to catch up here, and then we'll have a look at the object in just a quick second. All right. There we go. There we go. Okay, so let's get myself set up here. All right, so again, this is an entirely separate galaxy. Now, when you look up in the sky, right, you can see the Milky Way if you have dark skies, and that band of light across the sky is the plane of the disk of our own Milky Way galaxy. But everything you see in the sky, it's all part of the Milky Way. In order to really appreciate it, sorry, my headset just disconnected there. I should have it back now. But in order to really appreciate it, we have to see it from the outside, because our sun is just one of the hundreds of billions of stars within our Milky Way galaxy. Our Milky Way, again, is an enormous spiral galaxy. That's kind of what it would look like there from the outside. So we are again, our sun is just one of the hundreds of billions of stars within the Milky Way galaxy. Everything you see in the sky, with only a couple of exceptions, is all part of that. We're going to be looking at an entirely separate galaxy that is located 23 million light years away. And it is quite a beautiful one. It's one of my absolute favorites. Because although the Milky Way has some spiral structure, we can't really appreciate that because we're stuck inside of it. But this galaxy I'm going to show you is called the Whirlpool Galaxy for a good reason. It's kind of got a whirlpool shape to it. And just give me a quick second here to get that all set up for you. All right, so we are almost there. Almost on that target. All right, so it is located, I forgot to mention that. It is located kind of near the tail end of the Big Dipper. So very pretty easy one to find actually, if you know your sky a little bit. If you can find the Big Dipper, also known as Ursa Major, the Big Bear, just off its tail, just above it right now, is the Whirlpool Galaxy. All right, and here it is. This is straight from the telescope, and this is roughly what it looks like in the telescope. So again, this is an entirely separate galaxy system, actually two separate galaxies, and it's about, again, 23 million light years away. 23 million years for its light to reach us. And although it is faint, you can see that there is a spiral structure. And there's two brighter parts, the core of the larger spiral galaxy here, and then another separate core up above it. This is because these two galaxies are interacting. And let's take a longer exposure now. Again, this is kind of what it looks like through the telescope. Let's go for about 45 seconds to bring out some more detail. So what's going on is this smaller galaxy above is passing by the larger one, and in the process, the gravitational effects of the smaller one are tugging on the larger one and actually exaggerating that spiral structure. And so we call this kind of a galaxy a grand design spiral galaxy. That's a very fancy term for saying it's extra spirally. It's just got lots of nice tight spiral arms inside of it. And essentially, those spiral arms are like waves, or almost uh, areas of greater density where the stars are bunching up. And the stars are still moving in orbit through the galaxy, but the where they bunch up is where the spiral arms are. Just like if you're going down the road and you encounter an accident, but the accident's cleared, there's still a traffic jam before you keep moving again. It's where they bunch up that the spiral arms appear. And where all that gas and such bunches up, I got a little more contrast for you there. Where it bunches up, that is where you're going to get a lot of star formation as the gas comes together to form new stars. And that is why the spiral arms also tend to be brighter than the areas between, because there's more young, bright stars within the arms. You can also see that there's a faint bridge connecting the two galaxies here, like a tidal bridge. So the gravity of this galaxy, again, is tugging on the other one. It's actually acting to somewhat wind it up, and material is also kind of being flung outwards a bit. And eventually, given enough time, these two galaxies will merge together in hundreds of millions or perhaps billions of years. They'll merge together to form one great big galaxy. So that spiral structure is a somewhat temporary thing in the whole lifespan of the galaxy. All right, so again, this is M51, 23 million light years away, and it's about 70,000 light years across. Our own Milky Way galaxy is about 100,000 light years across. So it's a little bit, this galaxy is a little bit smaller than our own, although that may change when they merge together. They could also be more spread out or more compact. Doesn't necessarily mean there's more or less stars, but in terms of the diameter, this one we think is smaller than our own Milky Way. So this is a great example of a spiral galaxy. Our Milky Way is also a spiral galaxy, but probably not as tightly wound as that. And this galaxy is kind of, well, it's disc-shaped, right? And when we view a galaxy edge on, it looks very different. So that's what we're going to look at next. We're going to look at an example of an edge-on spiral galaxy, where we can't really tell it's a spiral because we're looking at it almost like a sheet of paper edge-on. And so that is the next one. This next galaxy is known as NGC 4565. It's got other nicknames such as the Knife Edge Galaxy, and you will see why. So I'm going to move the telescope again. Off it goes. I'm going to move the dome as well. Not as big of a move this time. It's not too far away from where we were just looking. Okay. All right. So again, this next galaxy, again nicknamed the Knife Edge Galaxy, is somewhat similar to our Milky Way. Probably more similar than the Whirlpool. The Whirlpool's pretty, but in the grand scheme of things, it's not all that similar to our home galaxy. But this one, well, our own galaxy would probably resemble it if we were to leave our galaxy and look back edge on. It would probably closely resemble this one in many respects. All right, so let's have a look at what the camera's seeing here. Almost got that set up as well, and we'll start off with a 8-second exposure, and here's the view from the camera. I haven't taken the picture yet. Here it comes. There it is. All right, so that's pretty close to what it looks like in the telescope with an eyepiece. We've got a brighter part at the center, yeah, and then we've got a line cutting through it, and you can kind of tell that that line extends off away from it. So again, this is an edge-on galaxy. If we were to view it from the top, it would probably have a spiral structure like the one we just saw, though not as tightly wound. But there's more stars at the center, and what we call the galaxy's bulge. You can see it kind of is not only brighter, but rises up a little bit as well. And we're gonna take a longer exposure. Let's again go for 45 seconds of exposure. Should be enough time to bring out all those details. And we happen to be viewing this galaxy almost perfectly edge on. Sometimes we view them kind of at 45 degrees or 30 or something in between. But I chose these two because the Whirlpool we're viewing almost face on, and this one we're viewing almost exactly edge on. So the galaxy is about 100,000 light years in diameter, but only about 10 to 15,000 light years thick. And it's located about 40 million light years away. 40 million years for the light to reach us. I think that's pretty far, right? The way I kind of make sense of those numbers is I look at the age of the mountain we're on here at McDonald Observatory. The mountain we're on is about 30 million years old. So the light took longer than this mountain is old to reach us. So we were seeing this galaxy about 40 million years ago. And now you can see more detail. We do have a satellite trail. The satellite happened to pass in front. That's what that line is there. So just kind of ignore that. But we do have a line of dust and gas bisecting the galaxy. So our own Milky Way has a line of dust and gas as well. That's most of when you see pictures of the Milky Way, that's mostly what they're showing you is the plane of the disk of our Milky Way. And the gas and dust is blocking the starlight. So we're just seeing that here, the same kind of a thing in a different galaxy. And it's in the darker area where there's lots of hydrogen and helium. And that's really where you're going to expect the most star formation, most new stars being formed from that cloud of gas and dust in there. All right, so we saw two very dramatic galaxies, if I say so myself. I think those are two very good ones. But the next galaxy we're going to look at is quite different in structure than the two we just saw, and our own as well. So this next galaxy is really something special. But at first, it isn't going to look like all that much. This next galaxy is known as Messier 87, and it made the news last year for good reason. But Messier 87 is located in the constellation of Virgo, and Virgo is it's up relatively high in the east at the moment. I'm going to move the dome again to align the telescope with the dome. And M87 is a good example of an elliptical galaxy. Elliptical meaning it's kind of just a big blob, really. It doesn't have any spiral shape, doesn't have anything like that. M87 is really just a big hazy glow of stars at first. It's actually classified as a supergiant elliptical galaxy, meaning, well, it's really big, and that super there is not there by accident. This really is an object of superlatives. It is one of the largest known galaxies in our universe. One of the largest galaxies we know of right now is the one we're going to look at right now. But how it got that big is by merging with other galaxies. Galaxies like we saw in M51, we saw other galaxies kind of spinning around each other. Eventually, they will merge together, and all that is left is one big hazy blob, and all the structure will have disappeared. All right, here we go. So we're going to start off here with a relatively short exposure of a few seconds. And here we go. Here it is. Okay, so at first, again, it's a hazy blob, right? But that hazy blob is the galaxy. Let's go for a little longer. It looks a little better than that. We'll go for 9 seconds. We'll take that picture again here in a second. So again, this galaxy got really big by merging more and more galaxies together. And this happens to be within a cluster of galaxies. All right, so again, big fuzzy blob, and if I take a really long exposure, it's still going to look like a fuzzy blob, just bigger. We've got another one over here as well. Again, this is within a cluster of galaxies, so there's lots of other galaxies nearby. Another galaxy here. But let's zoom in. Zoom in here. We've got a fuzzy glow, and then there's this little thing sticking out. Doesn't look like much, almost just looks like a smudge there. But that thing, that little thing you're seeing there, and you can see it again with the telescope, in my opinion, is one of the most awe-inspiring things in the entire universe. That line is direct evidence of a supermassive black hole at the center of this glow. So again, this galaxy, although it doesn't seem like it, is awe-inspiringly huge. Our own Milky Way has the mass of about 500 billion suns. This galaxy has over 2.4 trillion times the mass of our sun. It is enormous, and at the center of this enormous object is an enormous supermassive black hole. And I'm going to take a longer exposure, just like the other ones. I'll take it for 45 seconds. It'll refresh here in a second. But in the meantime, I want to show you a little animation to give you some reference. So again, that's what we're looking at right now, as seen from some imagery from other telescopes. Again, it's about 100,000 light years across, but instead of a disk, it's more of a sphere. This object also has lots of X-ray streams coming off of it, and you can see there's that little jet we just saw coming off to one side. There's also data there from the Chandra X-ray Observatory. That X-ray means it's very hot, very, very hot in that region. And as we zoom in, we reach the limit of what optical telescopes can show us. And the rest of the data here was taken from radio telescopes, such as the Very Large Array and the Very Long Baseline Array. And they're able to get much higher resolution. So again, this is false color, radio waves. This is actually one of the brightest radio sources in the sky. Zooming in more and more and more, eventually, when we zoom in towards the heart, where that black hole is, the origin of that little jet, we reach the event horizon of the black hole. And maybe some of you have seen this picture before. It was famous because it was released about a year ago. This is the first ever direct image of a black hole. The first image we've ever taken directly of the event horizon of a supermassive black hole. And that's a very tight area. Again, you're never going to reach that resolution with optical telescopes. That can only be attained by combining the data from many radio telescopes. And you can see that the sun would fit in the center there, and the orbit of Neptune is the outer circle. So even that is still a pretty large object. All right, so why does it have that jet? Well, actually, we don't really know exactly what's going on there. It's still a matter of debate within astronomy, what's causing this. But generally speaking, we know that a lot of matter is falling in towards that black hole. But just before it falls in, not gone all the way in, because if it goes all the way in, we're never going to see it again, right? But right around the perimeter of that black hole, a lot of mass is spinning around very quickly. It's spiraling in, and there's a lot of stuff there, a lot of gas, and it's rubbing against each other and causing lots of friction. And it's getting unbelievably hot, millions upon millions of degrees, much hotter than our sun, and developing an incredible amount of energy. There's also a magnetic field around that black hole. And that magnetic field and all that energy is basically shooting a jet, for reasons that aren't entirely clear, out perpendicular to the stuff following in. And that stuff is traveling at near the speed of light. And it's just funneled straight out the side, and basically obliterating a path straight out away from it. And that's what's causing that little jet. This little object emits 10 to the 13th times more energy in 1 second than our entire Milky Way does in 1 second. Again, that's 13 zeros, 10 to the 13th. So again, one of the most massive black holes we know of, the first one to be directly imaged, and of course we don't need super fancy radio telescopes in order to know the black hole's there, because we can see direct evidence of it in the form of that tiny little line branching off away from it. Oh boy, we got a big satellite across the path there. Lots of satellites around this time of night, and just refreshed. But now that I've zoomed out, you can also see there's another elliptical galaxy, big featureless blob of billions of stars over here, and another one. Because this galaxy actually resides within a cluster of many, many galaxies. And in fact, this galaxy is so massive that, and the entire cluster of galaxies around it is so massive, our Milky Way is being drawn towards this object. It's feeling a little bit of influence from the gravitational effect of this galaxy, even though it's 53 million light years away. So there you go. Maybe not the most photogenic object we could look at, but I think it's one of the most awe-inspiring things in the night sky. All right. But that is going to conclude our list of objects we're going to show you tonight. Again, if you want to see more, we do plan on doing more of these, showing you different things in the sky with new objects each time. And it kind of depends on the weather. So I can't give you a firm schedule right now, but we will definitely be doing more of these, as well as more on the moon, showing you some features on the moon, as well as perhaps the sun as well, showing you features on the sun safely. But at this time, if you've got any questions for me, I would be happy to answer them. And if you have any questions, please put them in the live chat, and our moderators will forward them to me. So moderators, if you have any questions prepared for me, if you would send them my way. Let's see, we might have a few here. Okay. First question from, okay. Ooh, that's a big name. Burhanuddin Kalkutawala asks, I think I did that right. How do people color pictures of the nebula like the ones when I Google it? Thank you guys for answering. You guys are awesome. Oh, thanks. Well, those color images come from either from color cameras or from integrating several images that are taken with a black and white camera like I have, but with filters. So the image I have here is that I just showed you is actually in green light. And what I did is I have a black and white camera because they're way more sensitive than color cameras. But I put a green filter in front of the sensor to cut the red light out. And I also did that because our human eyes at night are most sensitive to green light, but we don't see it in color. We see those green photons in black and white. And so I set up this image that way to approximate what the human eye actually sees, because the human eye is never going to see all that color you saw in those pictures online. But that's not to say the color isn't real. It's just that our eyes aren't sensitive enough to perceive it. So to create those color images, you need many hours of exposures. And you would take multiple images. The way I do it is I take a picture with a red filter, a green filter, and then a blue filter, and I combine them together to create the final color image, on the computer screen. So it's a multi-step process, and you're never going to really get that real experience live or anything like that. Okay, another question. From Foottrap10, how do we know it's a neutron star? We know that via different methods. One is because this neutron star is spinning very rapidly, and it's spinning every few milliseconds, and it's emitting this radio signal that we can pick up, and it repeats every few seconds. And that is actually a really incredible clue, because very few things in space that are that regular, where only something that is spinning and emitting this radio wave at a certain rate is going to cause that pattern. And we know that it's also a neutron star because of the temperature of the area around it. Neutron stars are incredibly dense, incredibly hot, and they heat up everything around it so hot it glows in X-rays. And a neutron star is kind of the only thing we can think of to explain how hot everything is around that area. We also know it from taking a spectrum of the object. We take the light and pass it through a grating to split the light up, and we can see the components essentially the chemical composition of an object based on the patterns it makes when we split the light up. And so that actually allows us to know what an object is made out of and a lot of other information. So we have a lot of evidence that there is a neutron star, a spinning neutron star in the center. All right, another question. What happens to neutron stars? Do they become new stars or do they just stay there? It came from Spencer Brown. They basically just stay there unless something else were to come along. Um, and generally, they are kind of just going to be neutron stars for an incredibly long time, billions of years more. They may slowly slow down or slowly start to cool off a little bit, but generally speaking, they're going to sit there unless something else comes along and runs into them. And if something else does come along and run into them, which is unlikely, but we know it can happen, it's probably going to cause another supernova. And it may be that in that second time, it doesn't survive at all and it's completely obliterated. We have seen two neutron stars merge together. We have detected that, so it can happen. All right. Another question. Is M51 younger than our own? From now, yes. Um, M51 is probably roughly the same age as our Milky Way galaxy, maybe slightly younger, but not significantly so. Roughly in the order of 12.5 billion years old. And generally speaking, it's not that far away in the universe, and in the grand scheme of things, at least. And we think it's kind of in our neighborhood. Things started to form around 12.5 billion years ago to form the galaxies as we know them today. How far apart are the galaxies from VIDS? I'm assuming you're meaning an M51, where those two galaxies were interacting. They are almost touching, but they're actually one is slightly below the other. We're viewing them face on, but one is actually a little bit staggered. So they're about almost 10,000 light years away, or actually a little more than that. Maybe more like 50,000 light years away from, but our line of sight makes them look like they're touching. What kind of telescope are you using? Reflective, refractive, infrared. That comes from Charles Johnston. I am using a reflector telescope, meaning it works using mirrors. And this is the type of telescope is known as a Ritchie-Chrétien. It's the same optical layout as the Hubble Space Telescope, just in a smaller package in here on Earth. But it's the same basic design. And it is using visible light. Again, I have a filter in here, so it's only allowing green light through. All right, another question from Chase Kincannon. I'd like to know what program you're using to show the photos from the scope, please. I'm using SharpCap 3.2 SharpCap. It's actually free. I have the Pro version. You can pay a little more, but yeah, SharpCap. You can Google that. Are there any deep sky objects that we could observe change over time? From Suntar Ramasamy. That's a great question, and in fact, the Crab Nebula M1 changes over time. Again, that object is only like less than 1,000 years old, and it's expanding really fast. And in fact, over year to year, you can actually see it grow by a tiny amount. It's subtle, but if you look back over decades, the difference is pretty obvious. We can actually see it grow almost in real time, not quite. I mean, if you sat there, you wouldn't see it, but if you come back in a year or so, it does look different. Okay, let's get some more questions in here. All right, they're sending more questions my way here in just a moment. Do you have any radio telescopes at the observatory? From Ben J. Yes, we do. We have a new one. It's a little over about a year old. It was now. It's called the McDonald Geodetic Observatory, and it's a big radio telescope to look at quasars, which are very massive and very bright radio sources, radio galaxies. And these quasars are billions of light years away. And this radio telescope is actually only looking at these objects for a brief period, and then looking at a different one, and then looking over there, looking somewhere else in the sky, continually doing this because it's not actually trying to study the objects. It's actually trying to measure exactly where they are in the sky as reference frames for us here on Earth. So just like how astronomers or let's say sailors hundreds of years ago, when they wanted to find their way, navigate and they're in the middle of the ocean, they look at the stars because the stars appeared as relative fixed points in the sky that they can use for reference. In reality, that's not good enough today for modern GPS systems because the stars do move a little bit and the Earth is wobbling around and moving through space too. So our radio telescope is looking at distant objects to serve as reference markers, and we hope that will improve GPS accuracy 10 times over what it already is. Well, it's a NASA partnership that we have for that project. Again, the McDonald Geodetic Observatory. So, all right, another question from Pete Nati. So is the universe expanding as the galaxies merge? Yes, so you may have heard that the universe is expanding. That's definitely true. Generally speaking, as time goes on, galaxies are getting further apart on the large scale. However, although the universe may be expanding on the large scale, on smaller scales, if two galaxies get close together, they'll merge. So gravity is stronger if they get close enough. And the expansion of the universe isn't enough to always resist that. So when you look out at the huge grand scale of the universe, you see lots of galaxies clumped together. You got a clump over here, the Virgo supercluster. You got another clump somewhere else, and the space between the clumps is growing because of the expansion of the universe. All right. Another question. What's the latest on whether the universe is expanding or contracting? As I just said, and that's from Gem Lenino. That is, we do think that the universe is expanding, and all the evidence is currently pointing towards that. The further away we look, the faster the galaxies appear to be moving away from us. The exact reason why is unknown. That's another project here at McDonald Observatory, is to try to figure that out. It's called our dark energy experiment. It's taking place on our largest telescope here. So we're trying to map out how fast distant galaxies are moving and try to figure out why the universe is expanding at an accelerating rate. Again, we're not sure why, but we're working on it. Okay, another question. Is the acceleration of the galaxy the same as the expansion of the universe, or are they separate events? Also, is the universe's expansion because of repulsive gravity? From Carlos Gutierrez. Well, the expansion of the universe and whatever's causing it to accelerate, we think are probably related. We don't know enough to be sure, but basically, the universe feels this force wherever you are that's pushing things away, creating new space, pushing things apart. Again, we don't know exactly why, but we don't really. I wouldn't say it's like repulsive gravity. You can describe it like that. It is sort of an anti-gravitational force, but to be frank, we don't know enough to be sure if it really is that. Whatever is causing it, we call dark energy, but that's kind of a placeholder name until we figure out more. So it could be this sort of repulsive gravity thing, or it could be something else entirely that we don't understand yet. Okay, another question from Julie Valadez. What is the most amazing thing you viewed while at McDonald? Most amazing thing. I saw Saturn through our 82-inch telescope here. It's much bigger than this one. And, I'd seen Saturn a million times before that, but seeing Saturn through that enormous telescope on a really good night blew my mind. It was just inspiringly beautiful. No picture could ever do it justice. So that was really incredible. Other amazing things, enormous bright meteors that break apart and shower into tiny little pieces, leaving trails behind them. That's almost every few months something like that happens. That just takes my breath away every time. All right, let's get some more questions in here. I got time for a few more. Let's see here. All right, I'm going to sift through a lot of these questions. Here's an interesting one. Is it possible for a black hole to suck up another black hole? Yeah, actually. Two black holes can merge together, and we think they just form one great big black hole. And we think we've actually detected that happening. Well, not here, not us personally, but we think that that has happened based on telescopes that are sensitive to gravitational changes, essentially, gravitational waves as they're called. Because when two black holes merge, like ripples in a pond, the gravitational effects radiate outwards, and we can actually detect that. And it takes enormous things colliding to make that happen. And we think the only things that could make that happen are black holes colliding. So it's very rare, but yeah, we think it can and has happened. All right, I'll take, let's see here, one more question here. Let's see, I've got a whole bunch to pick through. Um, here's an interesting one. Will the destruction from a supernova ever reach our galaxy? You can say that, I could safely say that probably not. I don't think we have to worry about it. Only massive stars explode in a supernova, only the really biggest do, and you have to be within a few dozen light years or so in order for it to be a concern. And within a few dozen light years of where we are in our galaxy, there's no star big enough to explode that way. So we're good. We don't have to worry about it. Certainly not in our lifetimes, and probably not for millions and more, billions and more years. Yeah, if the Earth goes out, whatever way it happens, it's probably not going to be from a supernova. Um, but that would be quite a way to go. It would be pretty exciting, I think. All right, that's going to wrap up our Deep Sky live tour for tonight. Thank you all so much for joining me. This is a lot of fun. Again, I love looking at things in telescopes and sharing it. So thank you again for joining us for this. And we will do more of these. Check our social media for dates. We'll post them on there. But in the meantime, clear skies, y'all. Take care, and y'all have a good night.